advanced over the years. So sadly, a couple of weeks ago, we actually lost Gordon Moor. This is very sad. It's a coincidence that he was part of the presentation anyway, but I think we've probably all heard of Moore's law, where he predicted that the density of transistors would double every 2 years. And that was pretty much true for a long, long time. He predicted that a very long time ago, and it's been true to form until quite recently, I believe. I think he revised it once, so we'll give him that, but it was pretty brave, target. So one thing that has made reverse engineering more difficult is that simple fact that devices have shrunk and the features have got a lot smaller. Things that you could see with an optical microscope 20, 30 years ago are completely invisible now. You can kind of just about see them, but you can't resolve, 2 tracks, or you could be looking at a piece of metal, or it could be 20 tracks of metal, individual lines. So this is kind of what I'm going to base a lot of this talk about, is what has changed in the last 30 years, how hackers would attack a device in the late 90s, early 2000s, compared with what you really have to have now. So if we look at the floor plan of the chip, you can understand what is going on there. And really, it's how I describe it. It's just like a PC. You have this big messy area in the middle there, and that's the CPU. The rectangular blocks are just memories of different types. There'll be a flash on there, there'll be RAM, there'll be ROM, and maybe some fuses. But the CPU is the kind of the engine, which is doing all the computational functions. It looks like a mess, but it's very, very carefully laid out. I can trust me on that. So yeah, something like a device like this is going to be hundreds of thousands of transistors on there, and it's maybe 2 millimeters squared. So it's there's an awful lot of functionality on there, but it's not cutting edge technology because it doesn't need to be. So yeah, you have within the CPU, you have hundreds of thousands of logic cells performing logic functions. There can be, like say, about 300 different cell types, instances, and they're repeated many thousands of times throughout the CPU. There can be variations on a NAND, for example. Could be maybe 10, 15, 20 variations on a NAND cell. Could be the same for NOR cells. Depends on what they are tailored for. So going from something that's just been a kind of an accidental thing to improve security, the shrinking of the device, there have been a lot of conscious efforts to lock people out of devices at a silicon level. So on the left, we'll see something from quite a way back. This is a kind of, it's not actually a secure device, but it's what you would expect from that era. You can kind of see from the top layer what is going on. The device on the right, this is much more recent. This is a device that's actually out there now, and it looks very different. There's almost nothing to learn from the top layer. You can't really access anything. Everything that we see there is either going to be a security shield or it's going to be power and ground. So there's nothing you can get to on the surface. And other tricks that manufacturers play with is standard cell camouflage. So we see, look on the right there, this is 3 components, 3 layers of components. You have the silicon substrate, you have polysilicon, and you have the contacts, which connects the metal on the bottom level to the substrate or the polysilicon. Looking at those components, you might say it's a NOT gate. It's probably not, because I'm not that good at reversing standard cells. It's been a long time since I've done it. So maybe that's a NOT, maybe that's a NOR. But you look at the components and say, how is it wired? How can it possibly function? When you put a 1 in, it spits out a 0, so it's a NOT. But what if you could make it look like a NOT, but it's actually not a NOT? So a lot of NOTs there. So that would be pretty cool, because you could have 100,000 standard cells, and maybe 10% could be one or the other. which is going to confuse the hell out of any extraction from the device. You're going to physically reverse engineer the device. You're going to end up with a list of the functionality, but it's just not going to make sense. Things will be wired up, but it just doesn't. It wouldn't function. It can't function because of the confusion. And if you have so many, you might have 10 cells, and there's each of those 10 cell types has like a brother, which is actually performing a different function. So you have that level of confusion. It really becomes almost impossible if you can't work out how they've done it. And it's very difficult to do that, in fact. So going back to a chip from a few decades ago, our little friend there, you can see the circuitry in the CPU. You can see that the metals are vertical on this layer. The layer beneath the vertical will be horizontal because it's a transport system. So you have one layer in horizontal direction and one 90 degrees off. So you the signal can get about the chip efficiently. So if we can see that with a very low powered optical microscope image, then it's going to be pretty easy to see in a high powered microscope. You can take a lot of images of that. You can make a huge resolution poster image, and you can see pretty much where signals are going. You can see that there's a memory there in the top left. There will be a memory. There'll be a memory on the left, down the left side. All the regular structures are memories. So really, using an optical microscope, you could trace, a track or a signal from one memory to another, and it might be of interest. It might not be. But so imagine if you could actually just get a needle on this chip and just touch the signals on the surface. That would be cool. But the chip is covered in glass, so you can't do that. Well, you can, but you have to use some chemicals. So as an example, this is what used to happen. Basically, you'd burn a hole in the package with nitric acid, just so you can get to the surface of the chip. You clean it. The chip is covered in glass. That is what the very top layer here is. No, you don't see it. But the very top layer of the cross section, this is just silicon dioxide and silicon nitride, just transparent glass-like materials. But there's one thing that will remove that material, and that's hydrofluoric acid. There's not much else that will do that. And it's one of the nastiest chemicals you could imagine, but it will remove glass. Dissolving glass is it's not going to be a nice chemical if it dissolves glass. So it's, but you make a hole in the package. You protect the bond wires that you see there. You protect the majority of the hole with something like nail varnish. It works very well, actually. It's very resistant to hydrofluoric acid. So you use the nail varnish as a mask. You leave one hole, which is where you're interested in, and you just add hydrofluoric acid, seconds at a time. And at some point, you're going to burn through that glass on the surface, and you will actually see the metal tracks. So that's cool. So you clean that off. You can take that back. You can solder it back on your board. You can make it run because it still works. It's all connected. You haven't damaged anything. And you would run it, and then you could put a needle on any signal you wanted, and you could just basically listen to the data. So this is what people were doing for a long time, very successfully. But the thing is, the most important thing is that things have shrunk so much. So back in those days, yeah, you had a tool set, which was, I would say, fairly basic. You could get your hands on maybe $10,000, $20,000. You've got a microscope, of course. You've got a PC. You can stitch your images to make a high resolution poster. You've got a chemical fume hood, which you need because it's going to be hydrofluoric acid and nitric acid. So you need to be safe, even if you're a hacker. And then you've got a probing station where you put the needles on the device. And you need an oscilloscope as well, of course, to read the signal, to make sense of it. But it's fairly basic stuff. You can imagine somebody who have that in the garage if they really wanted to. It's not like a huge, and I know plenty of people that have had this sort of stuff in their garage. Not me. So yeah, just to summarize the differences, really, yeah. Back in the day, in the 90s, no active shields at all. They didn't think that this sort of thing was possible, so they wouldn't bother to protect against it. Yeah, you can expose the top layer of the device and you can probe it at will with a probing station. There's no encryption. The memories are not encrypted on the device because, again, they don't care because they don't think anybody's going to do this. When you get a needle on the signal, it's going to be pretty robust because the features are large, transistors are strong, and yeah, it should be fairly simple. Nowadays, you have much more complex devices, so they're much smaller, much more layers of circuitry. Everything is encrypted pretty much now. If you buy a secure device now, it will have an encrypted ROM, the flash will be encrypted. I mean, everything's encrypted, but at some point there has to be clear data on the chip. Yeah, very small devices, very sensitive transistors. Yeah, you need to be careful when you probe the signal, you get almost nothing out of it. So you have to amplify it and condition it so you can actually make sense. But I've highlighted these top 2 points for a good reason. So because of those, you cannot use an optical microscope anymore. You can't resolve the features, so you have to use an electron microscope. And this is kind of thinned the field quite a lot, I would say, because not everybody wants to go out and buy a $500,000 electron microscope or a dual beam system like what we have at IOActive. And these things are, well, I'll show you what it looks like. Yeah, in the red bounding box, that's a dual beam. So in essence, we have a scanning electron microscope in there, which we need to take the imaged layers of the device. Okay. We have to remove the layers of the device to then image layer by layer. We can do all that with the electron microscope, and we can use various other pieces of equipment to remove the layers, like polishing systems. It's usually a combination of chemicals, wet chemicals, dry chemicals, like plasma etchers, mechanical polishing, and other techniques like ion beams to remove materials, depending on what you want to do. So for me, the most difficult part of the process is the delayering. The layers between circuitry or something like, a couple of hundred nanometers, a couple hundred nanometers, and across something that might be a few millimeters, it's very, very difficult to achieve. But if you're a hacker, you probably send your chips to China. And us? Yeah, the lady asked what kind of devices would I be delayering, or why would people do this? We want to do this to show what can be done and how we can protect against pirates. People want to protect their revenue. If you're Microsoft, no, I'm just after that for me. So I was, the bulk of my experience has been reverse engineering legitimately. This type of device for companies that want to make compatible products. So for example, the best examples are video game accessories, printer ink, which you wouldn't believe it, but there are like billion-dollar companies making third-party ink. And, you know, a lot of other things like, I think there's going to be more and more opportunities where people want to protect something, want to protect their kind of after-sales market, really. If you're Microsoft, you want to make a video game console, which they don't actually make a lot of money on the hardware itself. They make the money back off the games and the accessories, and they want all of that to themselves. So they're absolutely paranoid. Firstly, they don't want anybody making games that aren't licensed by them. I don't think that will ever happen, but also the hardware accessories, they want to keep for themselves for as long as possible. But there are companies out there that will want to reverse the secured elements that are in these accessories to come up with their own solutions. And yeah, same for ink. There's huge opportunities, and all the competitors want to be the first to have a compatible product to get to the market, because it's only them and the OEM. So it's incredibly lucrative business to be in, and in some countries it's legal. It's close. It's you could argue about it, but yeah, it depends on the country you're in. But usually it's accepted. Yeah, it's nothing. Yeah, you aren't stealing anything. Basically, if it's the only way you can make a compatible product and you do the work properly, you're not stealing anything. There's nothing really to stop you making something, as long as it's not going to damage the platform. Like if you're allowing entry for somebody to run code on Xbox, then that would be clearly illegal. But if it's only to make a compatible product, then that's okay, and it's not posing any kind of risk, security risk for the OEM. So yes, yeah, we need the SEM to take the pictures, of course, because they're not, you can't resolve them with optical microscopes anymore. And when it comes to doing an attack, like an extraction, you need a focused ion beam. So that's why we call it a dual beam. You have the electron beam to look at things non-destructively, and you have an ion beam, which you can image with as well, but it actually, you can cut holes, you can deposit material, you can deposit conductive material as well as insulator material. So if you have you know what the device is doing, you have the design in front of you, you can take a real chip and then you can change that design and make it do something that it's not supposed to. And that's what people do basically. It's either to access signals which are buried deep within the device, or it's to edit the circuit itself so that, you know, it's okay, don't send this data here, send it somewhere I can see it, where I can get to it and extract it. So that's a dual beam is a huge investment. And it's not like you can just pull somebody off the street and get them to operate it. It's not, and they're high maintenance. So, yeah, you can spend $2 million on a dual beam. You could pick up a used one for a couple of $300,000, but it's going to cost you $20,000, $30,000 per year just to keep it running. And you need somebody who can operate it, and you need somebody who can come and fix it when it goes wrong. So it's, for some people, it's okay, let's do this some other way. It's like the last resort to have to fully reverse engineer a device, which is an enormous amount of work, just to find that location or data bus where the code that you want to see, you want to extract, is running in clear, unencrypted. So yeah, to conclude, sorry.
Even if you reverse engineer everything, you got a similar product, aren't you in violation of like a trademark or a patent law or something?
I don't believe so. I mean, the example that I can give is when I worked for a previous employer, we broke the Xbox 360 authentication chip, or revenue protection chip, we call it. So we could therefore make any device that any accessory that we wanted. It was only us and Microsoft that can do it. They couldn't block our products because it was the same algorithm that generated the key. So you can't tell the difference, although you can't obviously sell it as a Microsoft product. You can sell it and it will work exactly the same as theirs. So they're not happy about this, of course. So they did block some products by using the fact that we sold memory cards that were a higher capacity than theirs. So they'd say anything over 512 megabytes, we're just going to update the firmware and just lock it out. So actually that is illegal, right? So what they did was illegal. We had millions of memory cards in the field, and a lot of unhappy customers. So my company that I worked for, we had to sue Microsoft. And of course they counter-sue because, oh, your joypads look the same as ours. And it's like, well, yeah, they kind of have to, you can't look like a can of beer or something, it's got to, people aren't going to buy it. It has to have the buttons in a certain place. It's certain things you can't really protect. So that's what happens. Yeah, there's sue, counter-sue, and it was settled out of court, basically. But yeah, you extract the key information that you need and you implement it in another device that you design yourself. So it's not like taking a chip and just reproducing it like you would imagine. And you could do that, but that would be, of course, highly illegal. So yeah, just to conclude, that sounds like it felt very fast. That was about 5 minutes, but yeah, I think the key thing is anybody can buy the tools, right? If you think you're going to make 10 million per year making ink cartridges that are compatible with HP printers, then it's a no-brainer. You just buy $500,000 worth of equipment and you get going. But it's not as simple as that. You have very complicated tools. It's a whole new realm. From using an optical microscope to using a scanning electron microscope, it's just not the same. You need a kind of background, you need experience, you need time, and you need the money to maintain it as well. So I think the amount of people doing this is very small these days. And there's a lot of tricks that manufacturers make to try and confuse things, to make things difficult. But at the end of the day, you got a device with hundreds of thousands of components, but they are components. It's just a machine. You can reverse engineer a machine. They can play tricks, but essentially it has to do the function so you can extract everything from it, because it's a physical thing. So yeah, if there is a reward, then people will do it. They'll invest the time and the effort and develop skills, bring in people that are, chemists, physicists to do this thing. It's not a dirty sort of garage job anymore. It's a much more professional operation. So yeah, it does happen. I think there's less people doing it now, but it's a real threat. So any more questions? Oh, not you, Greg.
Hi,
We have a question
most of
online.
these modern devices have this TPM chip like Apple phones or Android phones. Can they also be reverse engineered with these approaches?
Yeah, it's a very good question. And I probably should have addressed this, but yeah, you could do it with anything. It's the level of effort, really. It's possible to reverse pretty much anything, but how long is it going to take? And how much effort and time have you got to put into it? If it's a specific, like a secure ASIC, it's going to be something quite small. Like I've shown, it's going to be in the hundreds of thousands of logic cells. It's not going to be a huge, like a CPU. If it was something enormous, there are techniques that you can use to localize the part that you're interested in. You can kind of use techniques which will, transistors emit photons and heat. So you can kind of look at them or look through the back of the device while it's running, and you can get like signatures that will build up over time. And it tells you that when you're talking to it and asking it to do things, that the activity is taking place, geographically in a specific point. So maybe you only have to reverse a smaller part of it.
So Tony, what's your background? Mechanical or computer science or engineering?
I'm chemist by education. So yeah, yeah, everybody asks that question, and it's and most of the people that I've worked with will be either computer science background and they've kind of moved into this, some kind of electronics background, or physics or chemistry education.
Another question is, are people using deep processing technologies like this one to see chips that are behaving how they are expected and don't have any type of malware or spyware embedded? I'm not too sure I follow the second half of that question. Deep processing technology like this to see if chips are behaving and how they're expected to. I think it's the question of identifying malware, spyware embedded.
Yeah, well, you can have cases. This is interesting. This is another thing that we're going to be working on. You can have a device which is made somewhere and by a trusted supplier, but then somewhere along the supply chain, it gets infiltrated with bad material. So it can on the face of it, it can look the same package, it can look like the same circuitry, but if you add a small amount of circuitry to this device, it's like allowing a backdoor or allowing somebody to kind of monitor what's going on within the chip. So yeah, you can. It's like hardware Trojans, they call them. I think isn't that right? It's implants. Yeah. So it's.
I was just saying the other term that's commonly used is implants, hardware and software implants.
Yeah, you're basically slipping something in there, which isn't obvious. If you have something that has, millions or billions of transistors, and somebody adds like half a dozen logic cells, you're not going to see it, and it's going to be right at the bottom of the chip. So by physical inspection, you just can't do it. But deprocessing, yeah, you can use that to take a good example, a bad example, and you would, if you examine at the floor of the device at the silicon substrate level, if there's any extra cells or transistors, you have to see them at that level because they have to be on the substrate to function. So you do a scan of a good device and a bad device and do some kind of comparative analysis to make sure that it's 100% correct. Sorry.
Wait.
Go ahead.
I was just going to ask, so obviously nation states, particularly nation states that are interested in catching up and sort of maybe, semiconductor industries. What's more difficult for them? Reverse engineering chips, figuring out how the chips were layered in the first place, the chemistry, the layering process, or is it the machines that actually make them, that do the layering? What's the difficult? Like you make it sound like the reverse engineering of the hardware, for a well-funded nation state probably isn't that complex for them, right?
Yeah, I would agree. The bulk of pirates will just send samples to China and they'll get sent back the images. They do it very efficiently. They have a lot of people. I mean, for IOActive, we're doing things much smarter, trying to automate things so we can do this very cleverly. You take one chip, you remove one layer of circuitry so that hopefully 100% is visible. Then you image it once, you take off another layer and you image as you go down. In China, they'll have many, many samples and many, many people, and they will be manually polishing. So you maybe get 10% of the circuitry that you want from one chip, but it doesn't matter because somebody else's, they build this huge jigsaw together. And what you end up with is actually perfect because they've got so many people that are so experienced at this polishing and stitching these images together to make something that looks flawless in the end, but it's a lot more effort. Time-wise, I think it probably takes about the same as what we would end up doing, but it's just they have like 20, 30 people on a project at a time, all working very fast.
This is a significant amount of chemistry in each layer, right? So you mentioned some of the chemicals that are in some of the layers, silicon dioxide and things like that. Each layer has like...
Yeah, it's very, these days, very, very complex. That cross-section that I showed before was quite old. So you have silicon nitride on the very top, the passivation. Then you have all of the circuitry embedded in silicon dioxide. That's it, pretty much. The metal tracks are, in that case, was aluminium and tungsten. Aluminium for the tracks and tungsten for the interconnects, the vias we call them. And then you have different materials on the surface, at the foot of the sample, the footprint. Nowadays, the dielectrics or the insulators between circuitry layers have to be much better performed, much better insulators, called low-K. So it's very, very high performing insulator, and they're not usually, they're less like glass and more like a gel almost. These materials, and there are many, many more layers. So you look at a cross section and you see each layer between the circuitry is made up of several layers. So it doesn't matter so much for the deprocessing because you can usually use the same chemicals to remove it. If it's an insulator, you'd use HF, hydrofluoric acid to remove, or a plasma etcher, and it would do the same job. These days, devices with the circuitry is made out of copper. Many, many more layers and much smaller, of course. That makes things very difficult because the tracks are copper, interconnects are copper, and it goes copper all the way down. So you can't use wet chemicals because the chemical will just eat all the way through layer by layer and you can't control it anymore. So you have to rely less on chemicals these days to deprocess, more on things like ion beams. Plasma etchers are still used quite a bit, and basic mechanical polishing, but with advanced systems, more advanced systems. I think it's the hardest part for sure, is the invasive attack is still very difficult because you have to go through several layers with a focused ion beam, opening up tracks, getting to the points like surgery, you're kind of opening up several layers of circuitry, getting to the point that you want, but then you have to remake that circuitry. Otherwise the device won't work. If there's an active shield on top, that's what's there. It's a mesh which is being scanned the whole time to make sure that nobody's doing what we are doing. So if you cut a track open and then you tap onto your signal and you power it up, it's just not going to work. It's going to dump the flash because it knows it's been kind of attacked. So it's very clever. Yeah.
Yeah, I got a question on the, let's say if it's a FIPS 144-4 module or something, hardware encryption module, which is guaranteed to be unbreakable or, impenetrable. So is there like a self-destruct or something like that, which prevents this kind of reverse engineering?
Yeah, like exactly what I just said there. Almost all secure devices will have an active shield. So if it's still possible to bypass that, you make a hole, you cut a couple of tracks to give you access to where you want. But as long as you remake those tracks, the chip is not sensitive enough to sense there's been a breach. So you can't do a huge reroute of a track because the signal is timed. But if you kind of make them roughly similar, it's not straightforward here. So they, yeah, you can, if you understand if the shield is in bunches of 4 lines, 4 tracks, you can't just reroute one of them because then the tracks, the signal won't match. You'll have 3 hitting the opposite end of the chip at one point, and there'll be one slightly delayed because it's had to go further. I mean, sensitivity is incredible. So if it was that sensitive, you'd have to reroute the other 3 tracks. So it's roughly timed still, but there's always sensitivity, of course. They're not going to make things that are super, super sensitive because it probably won't work. We'll get a lot of failures, but there'll be a kind of certain amount of leeway where you can, all right, make a small reroute and then it will still work, but you can't go sort of, making huge incisions and rerouting and presuming that the device is going to work. But that's what basically happens. Yeah, it self-destructs, it erases the flash as soon as you power it up, and then it will never work again. Simply won't boot.
What do you think of Intel Management Engine?
I don't know.
Okay. Do you think Microsoft Pluton is necessary?
Microsoft, right?
Pluton, like their new security chip?
I literally don't even know anything about that. Sorry. You can tell me about it after.
Okay. How do you see AI changing your field when it comes to like processing the images and whatnot?
Yeah, people ask that question a lot as well, and I think absolutely, it's a smart way of doing all of this. Yeah, we do. It's not a huge amount of. It's more the analysis of the data in the end. You end up with a netlist, I think, but it's a flat netlist. It's just a list of functionality. It's not in any hierarchy at all. So I think there's a lot of potential for that to be used there. The stitching and the kind of image processing is not such a big deal. You need a decent PC, but it's not like you need a lot of RAM. You might have, didn't mention that, but I mean, one device, say something that we looked at recently, it might be 5,000 SEM images per layer. And you might have 10 layers of circuitry to kind of 10 layers of images to stitch on top of each other. So you might end up with like, a couple of 100 gigabytes of images. So you need a good PC to be able to stitch, 5,000 images together seamlessly. But I'm not sure how it could be applied to that, but certainly for the Netlist investigation, I think, or the processing of the Netlist, it would be advantageous. It will become more of a thing.
Tony, I have a question, and actually I have a question online too. The lengths that you're discussing here or describing here is very extensive. So, but a lot of the attacks against hardware doesn't need to go this far. I mean, as prior to this meeting we were discussing, I saw a presentation, just popping the EEPROM out, reprogramming it, putting it back in, and you have control.
Yeah.
Thoughts about that?
Yeah, absolutely. It would be the last resort. I mean, unless you're crazy, but there's a lot of other techniques like side channel power analysis, all these sorts of attacks, like non-invasive attacks that you would logically go through first to see what popped out.
So second question is, make sure if I say this correctly, so governments that may consider reverse engineering to validate that regulations are being met, so that companies are following regulations. So it's a question of, are regulations being met, and would governments do the reverse engineering to validate that, basically audit, I guess, is really what it comes down to.
I'm not sure they can do much at the moment, but certainly a lot of law enforcement agencies, governments are putting more effort into this, because mobile device unlocking, things like this, they need to be able to work out how to do this. Personally, it's a strange one. I mean, I've looked into this before, and it's a very, very complicated area to try and unlock or extract data from Android or a Apple secure element. And these are very, very complicated devices, and you could spend many months, years getting to a point where you could make a solution to unlock that phone. But then, yeah, it's probably another 5 iPhones have come out in that same time, and each time there's another layer of security. So it's very difficult. I think it's almost impossible to keep up, I would say, when it comes to phones, especially.
So I suspect that very much like encryption, this faces the same problem, as in it's how much do you spend to decrypt, and how much time can you spend at it? I think it falls into the same space, correct?
I think so, yeah. It's a big effort, even for a very simple device. But yeah, everything is possible, but it's like, really, is it feasible? Is the investment, it is feasible, but it's the level of investment and time, it's maybe just not realistic to go that route.
I had a question. You were mentioning the logic cell. So is that like an actual physical representation of the yes or no, or the logic path is what those are being built into?
Exactly.
So
yeah.
When you're reverse engineering, you're basically trying to see how somebody else laid it out, or something like that is the advantage that you're gaining.
Exactly. I mean, by studying the logic gates, you can work out by the components there and the connections, or you need to know where the input is, where the output or outputs are, and you can work out that if it's a high going in or a 1 going in, what it should be to come out, essentially. So you can have a not is the best, the simplest example of that. You've got a 1 coming in, you've always got a 0 coming out, or vice versa. The simplest example is a buffer, which just does nothing. It just extends the signal from one place to another. Then you have very, very complicated logic cells, which will take 4 inputs, and then the output will be can depend on the 4 combinations of 1s and 0s going in. There will always be a certain outcome to that. They can be huge. It's not like a couple of transistors. There can be 30, 40 transistors to make up something very, very complicated to process 5 or 6 inputs and then define the output depending on those conditions. But you can work it out all by looking at the physical components, yeah.
So you mentioned earlier that one of the applications, I guess, big application for this is creating compatible ink cartridges that are compatible with Hewlett-Packard printers and things like that. So when I go and buy my $10 set on Amazon, that company in whatever country, I guess, re-engineered the chip through the process, like what you're saying, so that they can create these.
Exactly.
Okay.
Yeah. And there's, I suppose, the bigger the fish you are, the faster you can react. And as soon as HP bring out a new range of cartridges, for example, and printers, then they'll get the hands on the printers, the cartridges reverse, because there's 2 parts to it. There's a host device in the printer. It's a whole system within the system. So you can't look at just the cartridge chip. You have to understand the chip inside the printer as well.
They have to kind of look at both sides.
Yeah, exactly.
Okay.
Yeah. So you're kind of extracting data from both sides to make the final solution. So they'll be, they will be knowing exactly when these printers come out, and they'll be getting their hands on them. But I think, to my knowledge, the latest HP solution hasn't been well, it hasn't been hacked. People are trying, and it's quite a few years. And there's a device in Xbox One accessories, and I think that's getting on for 10 years now, and nobody's actually hacked that device. So there's a lot of effort going into making these things safer, but and they'll be delighted with 10 years. I mean, the other solution for Microsoft One has been hacked. So there are products out there, but the actual device that was intended for use to secure the platform, it's not been done yet. So that's how difficult it's becoming.
So using a software malware as kind of a analogy, say for example, you discover that an implant has occurred during the supply chain. Are you able to do attribution by the technique of the implant or the materials used of the implant?
Yeah.
Can you do the attribution that way?
Exactly. I mean, if there's
Okay.
anything that's been added to the circuit, to the original design, you have to see it, and it'll be at a specific layer of circuitry, which is the substrate. So for example, you can take a device like we've done today, in fact, and you can just, you look at the top of the device and you can see there's something going on, but it's a lot of power distribution. There's nothing really interesting. If you want to get to the footprint of the device, you use chemicals again, and you basically strip off all of the circuitry on the chip. Then you clean it up, and then essentially you can see where every transistor has been placed. The transistor has to be on the substrate for it to work. So it has to be visible at that layer. The upper layers could be rerouted slightly different. That'll be more difficult because that would have to be a full layer by layer reverse engineer project. And then you'd have to probably look at the netlist to spot differences. But the easiest way would be to add circuitry, well, add extra circuitry, and that would have to be at the substrate, and it has to be visible.
So can you actually attribute it to the point in the supply chain where it occurred based on the technique used?
No, that would, yeah, it's gonna look, yeah, it would have to be yeah, you couldn't say that, no. You just see it. All you can say is something's been added. So many standard cells have been added. So there's extra functionality that's been added at some point. And there's only so many fabs will be making chips at that technology node. So it's not like anybody can be doing it. If it's there's only a few big.
Well, that's
big,
the point. There's only
yeah,
a few,
it would be.
so-
I think it would be impossible to tell. Yeah, where that had happened.
So what do you think is going to happen now that the United States is bringing back fabrication onshore? Do you think it's going to be any better, any different?
You'd hope so. I guess so. Yeah, I think it's a cool thing. It's really like it's quite an exciting and interesting time. I think at the moment there's so much going on and so much strategy going on, and yeah, you'd imagine there's much less opportunity for that sort of thing to happen. But I suppose anything is possible. If you have you have a designer, well, is anybody 100% trustworthy? I don't know.
Following up on that, so you're saying that the only way to add circuitry at the substrate level is during the fabrication process. You can't come in later and add something to it. This has to be done in manufacturing.
Exactly. You're correct. Yeah. I mean, there was one story I read a good while back on, I think it was a laptop, and there was somebody realized that something was not correct, but they couldn't see what was going on. Well, the components are exactly the same as they should be, but somebody added a passive component. I don't know if anybody else maybe I'm remembering this wrong, but it was basically a passive component, but it wasn't. It was a small IC. So it was like, wow, but so that is possible. You could add something, take off something that's just really a passive component, a resistor or a capacitor, and replace it with something that will do that job, but is actually doing extra stuff.
And other question is, as Apple has moved to its own silicon design, is the system on a chip just that much harder to understand because of the size, or is there anything
Mm.
about it that is easier because it's everything on one wafer?
Yeah, it's you know, these things are huge and it's tiny technology. It's going to take a lot more research to understand which parts of the device are doing what, I suppose. Then essentially, I mean, things are floor planned, so you might have, like in the big CPUs for gaming consoles, you can kind of, people know what is doing what. There's 8 CPUs there, and then there's other stuff. So it's very isolated blocks of circuitry with their own memory, and they're all kind of operating as a team. You don't need to reverse engineer all 8 CPUs. You just do one, and it's just a mirror image. So you'd, if you wanted to do that, but similarly, other parts that are doing special jobs within the device can be identified by just doing your research. And then you could just take that and just focus on doing a full reversal of that small part of the chip, if it's obvious. But the example that I showed earlier, there's a huge CPU there, and there's nothing really to show you that one part's doing anything different from the other. It's like completely plain almost. But other devices can be different. You could have a massive sea of logic, but you can see clouds that are definitely clouds of CPU that are doing specific functions. And by kind of working out where they go to, you can that can help you. But a lot of the time these days, they just distribute things evenly and far. So it means that you have to take it as a whole, which increases the time and the effort to, you know, that's the last resort really. So you can't work out what's going on in a specific location. You have to do everything, and you end up with a huge net list, and then you, it's a lot of, at the end of the day, you look for something absolutely tiny.
I think you're saying, is it N-list or Netlist?
Netlist, sorry.
And what is a Netlist?
It's just, I think one of my colleagues would probably explain it better. It's just a list of functions of the chip. John?
Yeah, so a good way to think about the net list is it is an abstract, high-level representation of what is burned into the silicon during the lithography process. So it's something that you can look at and analyze from a logical standpoint. And so if you think about traditional reverse engineering, this is a kind of intermediate stage when the software, where you're looking at the control flow and how things interrelate and the overall software architecture. So it's very similar to that. So this is very common. I like VHDL, Verilog. Those are common terms we hear talking about specific implementations of a net list.
Seems like it'd be a lot easier just to hack and find the designs than to re-engineer the chip.
Well, this is it. You could always ask for the designs, but yeah, on one occasion I was working on HP chips for a company that I worked for, the same company as the Xbox. This is like the second big breakthrough that we had. Similar kind of application. You have, yeah, as the video game platform, is a different manufacturer of the chip, but similar course kind of system. And we started to make it, or sell solutions for ink. HP get in touch, say, you know, we're going to sue you. And it's like, oh, okay, but why don't you like talk to us and we'll explain that we've done things correctly. And because they think that you've just stolen a net list, or you've stolen the GDS file, the design file for the chip. That's their first assumption. You know, it's a relatively small company based in the UK. How have they been able to, they don't believe it's even possible to physically take, 10 chips and reverse and end up with a design basically at the end of the day. But once, they did come over and we showed them exactly what we did, and they went away. And that was thankfully, it saves a lot of, if they understand that we've done things properly and we haven't stolen or paid somebody off, then it's okay. It's not a lot they can do, they can make a fuss and make it expensive, but they understand at the end of the day we've done things correctly. So yeah, it would be easier. Just find somebody at the fab that can sell you the.
Tony, thank you very much. I think you have one more. You had your question slide, which with your contact info.
Yeah, so this is me. If you're on LinkedIn or you tend to be more active on Twitter these days, to show the exciting steps that we are making in the lab in Seattle. So much work to do there. And thank you all for coming, and thank you to all my colleagues that have been so kind and come to support me. Thank you.
Thank you very much.